Hello friends, welcome back to another session of EC Made Easy. We are into our digital communication section. Here we have seen all the possible ways of encoding the digital signal and make the bandwidth in the limit so that transmission can be taken up easily. Later we have seen that once we are working with the phase, instead of having two phases, if we have four phases, then 2 bits at a time could be parallelly sent. Instead of two phases, if we had 8 phases, then 3 bits in a parallel we could send. So these are the different possibilities. They are called QPSK, 8PSK, and so on. And then this concept went on. So overall, what are we doing here is one channel is used for transmitting a signal. So we have a transmitter and then we have a receiver. So for transmitting from transmitter to receiver, so we are using one channel. In this one channel, this is the encoded signal is modulated using AM, and that is demodulated at the other side and then decoded and continued. So here we have one channel used for this operation. In this one channel, we were working with multiple bits parallelly transmitting, either using QPSK or 8PSK or QAM or many such possibilities. There is other way of working is when you are working with a one channel. This channel has got a bandwidth delta F available to it, and this delta F available bandwidth, so this is our frequency axis. So this available delta F was used to modulate the encoded signal. Now there is another way of increasing the throughput is, instead of using one carrier, we can divide this into subcarriers. And these subcarriers, so make sure that they are orthogonal to each other. That means this is a F1, F2, F3, and so on up to Fn. If the band used for one channel is divided into, say, n sub bands, each one having a F1, F2, and so on, then whatever this subband can further be used to modulate. So each one can modulate 1 bit of information. So we are getting information in the form of bits. These bits are encoded using any of the schemes, and then the different bits are modulated using different subcarriers. So this way, if there are n subcarriers, then for n subcarriers we can have n bits being transmitted parallelly, because this is talking about one channel. One channel is this bandwidth, this bandwidth is divided into n sub bandwidths. So each of this subcarrier can be used to modulate 1 bit of information. So in that we can now parallelly send n bits of information per unit time from transmitter to receiver. The only condition required is they should not interfere each other. So whatever information this is carrying, it should not be disturbed by this. Whatever this one is carrying, it should not be disturbed by others. So that is possible only when these signals are orthogonal. That means one carrier has no effect over other carrier. So if we can find out the carriers which are orthogonal to each other, so you find n orthogonal subcarriers, and then each subcarrier can be used to modulate 1 bit of encoded data, and that way we can make sure that any given instant n bits are parallelly transmitted through this. So on the other side, yeah, we require the receiving side, we require demodulators to accurately demodulate each one separately. So we need n demodulators separate, and they should be in a position to distinct between the subcarriers. So they should mean about their own subcarrier, should not be disturbed by other subcarriers. So that if you take care, then we can make sure that n bits at a time can be transmitted over a single channel using n orthogonal subcarriers. And this process or this method or the technique is called the orthogonal frequency division multiplexing, or in short we can say OFDM. So it's a very much in use in the mobile communication, 4G, 5G and all. So OFDM is one of the key components in improving the efficiency of the system. So many more such things to come. So keep waiting. Thanks.